All right, video number 4. So looking at kind of graphs of mass spring systems. There's no pendulums here. We're not talking about those yet. Just looking at mass spring systems. Now that means it could be a horizontal harmonic oscillator or it could be a vertical harmonic oscillator. And so we could have, I'm going to zoom in a little bit over here. Maybe it's something like this, and then we got some spring going like that, and we have our purple box, and that's it. And it goes back and forth and back and forth, and maybe we say that right here maybe is our equilibrium point. And if we ignore friction, so there's no friction chase, then maybe as I stretch it over so that my box is, I don't know, maybe let's say it's over here. There'll be some restoring force. So I pull it over here. I'm doing some work. I'm exerting a force over some distance. So we could say that this is like our positive amplitude value. Then there's some restoring force going opposite to me. And then if I let go, that potential energy that's stored in the spring is actually going to be converted into kinetic as it sweeps over here to the left, and then it'll be at the maximum kinetic energy here because the spring will be relaxed. The spring is at equilibrium. And then as it moves towards the left, it'll slow down more and more and more until it is actually about the same amplitude in the negative direction. So this would be maybe my negative A for it. Now the same exact thing could be said for a vertical one. Now way back last semester, we hung a little spring from like a hook, and we said that, well, maybe this was the relaxed length for the spring originally, if the spring is just kind of alone, but maybe we hang some block from it. And if we're hanging a block from it, that means that the spring, oh, come on, is going to stretch from its equilibrium point, and now the box is going to be here on it. But now really with the box, this is our equilibrium. This is our new equilibrium with just the mass on it. So I mean that it'll just kind of stay about whatever the heck this vertical equilibrium point is, kind of right here. And then maybe I pull the box down, and I pull it down over here. And that means then that maybe our equilibrium would be, and I'm going kind of from the center of mass for all of these just as a heads up. That's why I'm putting the equilibrium here. I could have chose to say the equilibrium is here at the left end, and then I'd have to say the amplitude is at the left end and then the left end, and all our distances would actually be the same. And then we just have the same exact kind of motion. So as I pull it down here and I let go, it'll move up until it's at the maximum speed at equilibrium, and then it will keep going up to about the same. Oops, let's make those all purple. There we go. So then it doesn't matter which you call negative and positive, but if we said that up is the positive y direction, well, then this would be our positive amplitude, and this would be our negative amplitude. So just kind of now that we got that out of the way, hopefully you're not feeling like Andy here. If you're not a Parks and Rec fan, you should check it out. But ask me the questions. A staggering amount of people do not go to office hours and don't send any emails, and it's a little scary considering how many questions I usually get when we're like in a classroom together. But I don't get them now. So hopefully you got your kind of AP equation sheet out. Since we're talking about simple harmonic oscillators, we kind of need this one. And then this is kind of the other convenient one right here for our period equation. And then we have these two, one's for a pendulum, one's for a spring. We only really care about this one since it's just asking about mass spring oscillators, or at least it says in the title of this little kind of quiz. So I'm going to just rewrite our equation here. So the period for a spring is 2 pi times the square root of the mass over the spring constant. And we're told that identical blocks, so that means the mass is the same, and they're hooked up to ideal springs, oscillate on a frictionless surface, and the motion of the blocks is graphed below. and it's saying, why are the periods different for the two of them? So we have two blocks, and it doesn't matter whether they're vertical or they're horizontal like this. But we just have two setups, and it tells us here that the blocks are identical. So I'm saying, why the heck are the periods different though? Well, if we look at this first one, I see that, well, both of them are starting actually at a crest. So we go crest to, well, crest. So this one has a period of 0 to 4. So the period for this one, and this is A, period for A is 4 seconds. And period for B is 2 seconds. So, well, one of them has twice the period of the other. So it turns out that, well, if one of them, if they have the masses are the exact same, we can kind of rewrite these equations here and kind of look at it in math terms, if you'd like, over MA over, but it says the blocks are identical. So really, we don't need MA. We can just put M. So that means the only thing that really can be different are the springs here. And then the period for the second one, for block B, we still have the same mass because they're identical blocks, over the spring constant for B. Well, it turns out that B is a smaller period. Well, what would have to happen here with the equation to make a smaller period here on B? Well, to make a smaller period for B than A, we would need K to be bigger. So, for instance, if K was, I don't know, 4 originally, or let's say that for this one it's 4, square root 1 over the square root of 4, so 1 over the square root of 4, that would be 1 over 2, so we'd have like a 1 over 2 really coming out of this square root. If this one was, I don't know, 16 instead, well, square root of 16, that's 4, right? So 1 over 4, that's going to give us a way smaller period here. So really, the answer to this one is that for the period of spring B to have a smaller period, it needs to have a bigger spring constant, because the spring constant is in the denominator. It has to have a bigger spring constant. And there's option B. Okay. Now, the neat thing is that since we actually know the numbers for it, and we could just kind of set the m's equal, we actually could have found how much more it is, right? So if one of these is 4 seconds and one of these is 2 seconds, and m's are the same, we could actually kind of solve for KB in this one, and then solve for KA in this one, and then like actually kind of go in, or not actually, I take that back, sorry. We could have gone and set, since TA is twice the period of B, right? So really I'm saying that since the period of A is 4 and the period for B is 2, that means then that the period of A is equal to twice the period of B, right? So really then, if I multiplied this one by 2, and that means I'd multiply this whole side by 2, I could set this right side equal to this right side, and I could solve for like KB in terms of KA, because now the left sides will be equal, so the right sides would be equal. But it's not really asking about that here, so I'm going to skip that, just kind of food for thought. So let's look at our next one. Now we can kind of speed up a little bit. So it says 2 blocks connect to identical ideal springs. So wait, in 3 we had identical blocks and ideal springs, so the springs were different and the blocks were the same. Now this one, we have the blocks are different, but the springs are the same. It's still frictionless surface. We're still given a graph, and it's saying, why are the periods different? So actually, it's asking us the same question, but the only thing that changed is what's the same and what's different. So we have period for a spring is still 2 pi square root of m over k. But now the springs are identical. So that means that the k part here is constant. K is constant for both, so it's the same k. So rewriting these, we still have the period for A is equal to, now the masses are different though, so we have m, whoa, that's not an m, m A over k, and then the period for mass B, we have 2 pi mass B over k. And if we look at these, I can kind of see that, well, they both start at crests again, And if we're looking at B, I guess to start, I go from there to there until it repeats, right? So crest to crest, we've gone a full cycle. So if this was like a bowling ball on a spring and I picked it up above equilibrium, like we've kind of done in class, and then it falls to the bottom and it stops, for instance, and then it turns around and comes back up. Well, it's back at the top again. So we have the period for B, we have 2 seconds, and the period for A, well, we have 4 seconds. And so it turns out that the period for A is bigger. Well, surprise, it's the same period as the last question. The only thing that's different is the amplitude of B was smaller in the last question. The amplitude is 1, and now the amplitude is 2. It's actually the same value, though. And since these equations have amplitude nowhere in them, this graph or this question is just trying to mess with you, essentially. You don't really actually care about the amplitude in this case, or in this case, really. So looking at it, if A has a longer period, well, what has to be different between the two? If the spring constant's the same and 2 and pi are the same, well, MA must be bigger, right? If we have a bigger thing up top, we're multiplying by a bigger thing, we're just going to get a bigger number. So if for, I don't know, B, let's say this was 4 and this one was 16, well, square root of 16, that'd be 4. We're going to be multiplying this whole thing by 4 over here. And if this one's 4, we're going to be taking the square root of that. So we'll get 2 multiplying by 2 versus multiplying by 4. Well, multiplying by 4 is going to give us a bigger period. So it turns out that A does just have a larger mass. All right. Now again, they kind of switched it up again. 2 identical blocks. The blocks are the exact same here, connected to ideal springs. So the springs are different. Frictionless surface. Why are the periods different? So I'm just kind of messing with you now to see if you're really getting this. I'm asking the same question. I just gave you a different graph. So looking at it here, let's use yellow, I guess. So if we're looking at A, we start out as a trough at the bottom, and until we repeat, so right here, well, 0 to 4, okay, so our first period is 4 seconds again, and our second one, till it repeats, that's 2 seconds. Oh, there's a common theme here. These graphs actually are kind of the same in regards to the periods, at least. And just out of sheer laziness, we're just going to take this and copy it. I don't know if this actually saves time or not, but it feels like it does because I'm writing less. Okay. And so think about this. Based on the ones we've already kind of looked at, and saying that the blocks are identical. The blocks are the exact same. So really this A here can go away. And the B here can go away because those are the exact same. But we have different springs. Gotcha. So what has to be different here? If A has a bigger period, A has twice the period, what must be the case? Well, if A has a bigger period, that means it must have a smaller spring constant, because if we have a small thing in our denominator, our whole fraction here will be bigger. And it doesn't matter that we're taking a square root. If our number is bigger, we're going to get a bigger answer. It doesn't matter if you're taking a square root or not. That just affects like the actual number of it, but it doesn't change the size kind of relative to the other. So looking at this one then, well, we obviously have that if A is bigger because it has a smaller spring constant, you could equally say that B is smaller because it has a bigger spring constant. And so the only reason I'm choosing to look at it that way is because that actually matches our option C here. B has a shorter period, so smaller period, because it has a bigger spring constant. So if I have like, I don't know, let's say I had 100 right here in the bottom, well, I'm taking the square root of 1 over 100. So that means really I'm dividing this whole thing by 10. So it's going to make it a lot smaller in the long run. So we just have a big number in the denominator. So it's going to make us have a small period. And now It's kind of alternated the same way again. We still have two blocks, identical ideal springs. So that means that K's are the same. We're again still on a frictionless surface, and it's asking why are the periods different? Oh, you're kind of getting the theme here now. I bet at this point you could probably look at one of the previous ones we've done and kind of figure this one out. But we know that we have period of A is 2 pi square root, and the blocks are different, it says. So mass of A over, and they have the same spring, and then period for B, 2 pi square root of mass B, because the blocks are different, over K, because they're identical springs. So that means K is just the same. K is just some constant value. They're like identical springs. And why are the periods different? So looking again, well, this one's kind of interesting because we finally have like a very significant difference. If we're starting here at kind of this amplitude of 3, this maximum displacement for graph for block B, at least I chose to look at the purple, and we finally repeat over here. Well, this one has a giant period of 6 seconds, okay? And then this one has a tiny period, of 1 second. So it has 1/6 the period of block B. So if we're thinking about it, and the springs are the exact same, what is different? Well, it must be the blocks. And if we think about it, which kind of block, a bigger block or a smaller block, would give us a bigger period? All right. So if we want to have a bigger period, let's just think about it. Let's kind of go back to our picture, because I think some people are probably sick of the math. So if I kind of sketch just a little picture here, and this is just kind of, let's just assume it's horizontal, I guess. I just at least chose to draw it horizontal, and I have kind of this little block here, all right, and it has mass little m, or I had some very similar system, and let's say now I have like some wumbo block of mass big M, all right? Well, if mass is really kind of thinking way back to unit 2 when we're talking about like inertia and Newton's laws, well, it's way harder to push a semi-truck than it would be to push like one of those little plastic kiddie cars that you maybe rode around in when you were like 4, right? And the difference is because the masses are very different. They have a different inertia, and inertia is just the fancy word for like stuff, resistance to movement. Newton's first law says something at rest will stay at rest until like an outside force acts on it, or something in motion will stay in motion until something acts on it to change it. Well, thinking about it, if we had both of these moving, right? Both of these were moving at the same speed, but the same spring is acting on them. Well, if both of these have the exact same spring acting on them, K, they're both going to apply the same force, F equals KX, right? Well, if we have some giant block here and the same force is getting applied to that, is this small block, well, the big block isn't going to change its motion very quickly. It's going to just keep like sliding on. So if I had this giant block and I pushed it to the right, it's going to just keep going. Actually, let's kind of circle all of this here. And I kind of pushed to the right. This whole thing, I didn't want to get all of it. I just wanted to get the spring part with it, but maybe this won't work. That won't work, actually. Bummer. Well, it turns out that this block would just keep sliding. It'd be like a semi-truck, like a freight train, and you're trying to stop it. It would just keep going and going. And then eventually it would stop, and it would turn around, and it would be really, really slow because there's all this mass that is just really hard to kind of change the motion of. But if we had this little block and I pushed it to the right, well, this spring is able to actually kind of have more of an influence on it. So maybe this goes out and then it flies back, and then it smushes the spring together and then pushes it back, and it goes back and forth, and it does it pretty rapidly instead. And so maybe you're still going like, well, isn't there math on that too? Yeah, we could have talked about like, well, force is mass times acceleration. And if the left sides are the same, you could set the right sides equal. And so then like a big mass is going to have like a small a essentially. But really, I didn't want to look at it that way. I just want to look at it kind of in regards to kind of these equations up here. Well, because block B has such a small period, block B must have just an utterly massive, mass, right? So it turns out that for this one to have such a larger period for block B, it has to have more mass. Or in other words, block A has to have a smaller mass. So we're kind of looking for either of those answers. I see block A has more mass. That's not true. We said it has to have less mass. Block B has more mass. So there we are. And now this one. Wait, this one looks just like this one. Okay, well, let's read it at least. 2 blocks connected to ideal springs, frictionless surface, which has a larger frequency. Oh, that's the difference here. Okay. So this one isn't about the period, it's about the frequency. Well, we already know from before, their periods are 6 and 1 second. So looking at it, we can just kind of throw that in. Boom. Boom. T A is 1 second. T B is 6 seconds. And now, well, we know from that other equation on our equation sheet way up here, that one, that period is the same as 1 over the frequency. Or if you were asking, if it was trying to find like an angular velocity, you could kind of relate that too, but we don't need that now. We just know the period and it's talking about frequency. So if period is 1 over the frequency, period is 1 over the frequency, well, we don't even need to do any of the spring constancy stuff, at least yet then. It's just asking which has a larger frequency. Well, TA is 1 over FA, and TB is 1 over FB. So we could kind of look at it that way. But in all honesty, it seems more helpful to get the F alone since you're trying to find F, really, right? So all I would do, and I think I talked about this in a previous video, maybe your algebra teacher said like, well, we multiply by F here and we multiply by F there, then like the F's are gone, right? And then you have F times T, and then we divide by T on both sides, and then the T's go away, and we have a T down here. Sure, that's totally one way to look at it. That seems like a lot of unnecessary kind of writing in my book. So I would just say that period is 1 over frequency, and then we can just switch these spots because I multiply F over, and so it's up here, and then I divide by T, and so it's down there. So frequency is 1 over the period. So kind of getting rid of these, I think this is much more helpful. FA is 1 over TA. So that's just 1 over 1 second, which is the same as 1 hertz. Hertz is just like number of cycles per second. So it's 1 over second. You can kind of think of this as like cycles per second. That's like a really convenient way that I would recommend kind of thinking about it. And then looking at our second one, we have 1 over 6 seconds. Well, that gives me 1/6 hertz, or what is that on the calculator? That's like what, 15% or something like that. 1 divided by 6, that gives me like 16.6 or 0.166. Okay, so let's just say 0.17. So the frequency here would be 0.17 hertz. Well, when it comes down to it, then which one has a bigger frequency? Well, obviously block A, it has 6 times the frequency. Now, here's the funny thing. You could have not done any of this math. You could have just solved this by looking at the picture itself. If you go, well, which one has more cycles in 1 second? Or even, which one has more cycles in just whatever time frame I'm choosing to look at? Well, you could have said, well, let's just look at from 1 second to 6 seconds. Well, this one has 1 cycle. Okay, so its frequency is, well, it's just 1 cycle in 6 seconds. So it's 1/6. That's what we just got here. And you look at this one, you go, well, we have 1, 2, 3, 4, 5, 6. You go, oh, well, obviously that one did 6 in 6 seconds. This one did a sixth in 6 seconds. So block A, this blue one, has a higher frequency. It does more in whatever time frame I choose to look at. Now, typically frequency is just in per 1 second. So you look at this one and go, this does a full cycle, and this does way less than a full cycle. So you could have just looked at literally that and said A. So I hope that helps, folks. Let me know if you have any questions.